You ever wonder how computers actually talk to each other? I mean, it's not English, that's for sure. It's all numbers. And today, we're going to crack the code. A secret handshake, really, between two of their most important languages, Octal and binary. Now, I know that sounds kind of complicated, right? But what if I told you there's a super simple secret that makes the whole thing just click? Let's dive in.
So you've got these two different languages. Over here you have Octal, which is base 8, and over there you've got binary, base 2. I mean, that's the absolute foundation of everything in computing, right? Just ones and zeros. At first glance, they look completely different, but here's the thing. They're actually super closely related. So the big question is, how do you build a bridge from one to the other? Well, that's exactly what we're going to figure out.
Now you're probably thinking, oh great, here comes the heavy math. You know, long division, remainders, all that stuff we loved in school. But nope. The key to this whole thing, the entire conversion, it's not some crazy formula. It all boils down to one single number. Just one. And that number? It's 3.
See, this isn't about just blindly memorizing a bunch of rules. That's boring, and you'll forget it anyway. This is about understanding the why, seeing the beautiful, simple connection between base 8 and base 2. And trust me, once you see that link, the whole process just makes sense. It's not just easy, it feels, well, obvious. And here it is. This is the big reveal, the whole secret. 8 is just 2 to the power of 3. That's it. That simple little equation is the master key that unlocks everything. The base of the octal system, 8, is a direct power of the base of the binary system, 2. And that little number up top, the exponent, that 3, that's our magic number. That's the secret.
Okay, so what does that power of 3 actually mean for us? Well, it means that for every single digit in the octal system, there is a perfect corresponding group of exactly 3 digits in the binary system. Think of it like this. One octal digit holds the exact same amount of information as 3 binary digits. And it's that perfect one-to-one mapping that makes this whole conversion process, well, honestly, it's beautiful. It's so simple.
All right, so we've got the theory down, we understand the why. Now let's get practical. Let's talk about the how. We're going to take this amazing principle and turn it into a super handy tool, basically a cheat sheet that's going to make converting from octal to binary practically instantaneous. It's like having a perfect little translation dictionary.
And this is it. This is our octal to binary lookup table. It's the practical version of that 8 equals 2 to the power of 3 rule we were just talking about. Just a simple chart, right? Every octal digit, from 0 all the way to 7, has its own unique 3-digit binary code just waiting for us. So let's take a look. It's pretty straightforward, isn't it? 0 is just 0, 0, 0, 1 is 0, 0, 1, and you can see how it goes all the way up. Take a look at the octal 7, for instance. Its binary code is 1, 1, 1. That makes total sense, right? It's the highest possible value for one octal digit, so all 3 of its binary bits are switched on. Seriously, this little table is the only thing you're going to need.
Okay, enough talk. Theory is great, but let's see this thing in action. We're going to walk through an example, step by step, and you're about to see just how ridiculously easy this is.
Let's take the octal number 243. First thing we do, we literally just break it apart. We've got a 2, a 4, and a 3. Easy enough. Next, we grab our cheat sheet. We look up the 2. That's 010. We look up the 4. That's 100. And we look up the 3, which is 011. And now for the final step, which is probably the easiest part of all, we just squish them all together. And bam, there's our binary number.
And just like that, we're done. The octal number 243 is the exact same thing as the binary number 0101000011. See? No crazy calculations, no long division. You just separate the digits, look them up on the chart, and stick them back together. It's really genuinely that simple.
Pretty quick, huh? Let's do a couple more, kind of rapid-fire style, just to make sure it really sticks. This'll prove that the method works for any octal number you can throw at it, big or small.
Okay, let's look at 105. That's just 001 for the 1, 000 for the 0, and 101 for the 5. Put them together. How about 76? Well, that's 111 and 110. Done. 31, 011, and 001. Easy. Even a bigger one, like 567, it's the exact same process. It doesn't get harder, you just do the lookup one more time. It's just rinse and repeat.
So, if you walk away from this with just one piece of information, let it be this. It's the whole key. One single digit in the octal system can be represented by 3 digits in binary. That's the golden rule.
Everything we just did is built on that one simple, powerful idea.
And that kind of brings us to a really cool final thought. So we've established that octal, which is base 8, needs 3 binary digits because, well, 8 is 2 to the power of 3. So what about hexadecimal, base 16? If you apply the exact same logic, how many binary digits do you think you'd need for that? Something to think about. Thanks for tuning in.